Welcome back and continuing our discussion of buffers. I'm going to illustrate with two examples, one where there's no buffer present. I'm adding an acid to water and the pH will plummet. Normal water has a pH close to 7. And in this problem, we're going to prove that the pH goes down all the way to 2. So what happens here, I'm adding 0.01 moles of HCl to 1 liter of water. So you have to know that the definition of a strong acid is an acid that reacts completely. So you must react all of your HCl in this problem. What's it going to react with if the only thing you put it in was water? Well, water's the only thing. HCl reacts with water to create Cl minus and hydronium. We start with adding 0.01 moles to 55.5 moles. That's how many moles of water are in 1 liter. And you didn't have any Cl minus or H3O plus before you started, although you people knowing neutral water started with 10 to the negative 7 moles per liter of hydronium, but that's trivial compared to what we're creating in this problem. You must react all your HCl. You will get rid of 0.01 moles of water, and yes, you still have 55.5 moles. Water's concentration is constant in this problem. Cl minus, I don't care how much I make. It does not affect the pH in any way, shape, or form. Being an incredibly weak base, it just sits around. The most important thing you generated was 0.01 moles of hydronium in a 1 liter solution. There is the molarity, there is the log of the molarity, and that's 10 to the negative 2. If you have 10 to the negative 2 and you take the log of it, you get negative 2. Remember, the P means multiply that by negative 1, and you got a pH of 2. So in an unbuffered solution, if you add acid, the pH goes down a lot. It went from 7 down to 2. In my next example, I have a buffer present. I'm adding 0.01 moles of HCl, same amount as the previous problem, to a solution that's called a 0.025 mole per liter solution of sodium acetate. It's not a buffer yet, but when I'm done, it will be a buffer. pKb of water is 17. I took 14 minus the pKa of water's conjugate acid, 17, and the pKb of acetate is 14 minus acetic acid's pKa. Yes, that's the conjugate acid. And 9. Now the question is, which of those bases is going to react first with HCl? And the answer is not even close. Do not react HCl with water when you have a base that is, let's see, 10 to the, let's see, the difference is 17 minus 9 is 8. That's 10 to the power of 8 times more basic, which is, if my math is correct, 100 million times more basic. Please react the acid with the thing that's 100 million times more basic. I'm starting with 0.025 moles of acetate. It says right here, 1 liter of a 0.025 moles per liter solution. And I'm going to react all of my HCl. Every time you react an HCl, you lose an acetate. So you're going to lose that amount of acetate. You're going to gain this much Cl minus. I don't care. Cl minus is superfluous in this problem. It has no meaning whatsoever. You generated acetic acid. Now I know I have a buffer. Do you know why? I have a mixture of acetic acid, pKa 5, and its conjugate base, pKb9. Both are weak. Weak acid over here, weak base here. The buffer, I know right away, will be the pH of the buffer will be close to 5. How did I know that? It's going to be close to 5. I looked back here at my Henderson-Hasselbalch. The pH of a buffer is close to pKa and the log of the ratio of the base to the acid. So it's always going to be close to pKa. Remember that when I ask you again later in the next 5 minutes. All right, here's the part you do on a calculator, which you'll never do on the test. You take the log of the molarities, 0.015 moles per liter and 0.01 moles per liter, and you plug it in and you get 5.2. As promised, the number is close to 5. Is that magic? No, it's not magic. That's what buffers do. Trying to get my pen on here. There we go. Close to 5. That's the pKa, 5, right? That's what buffers do. Okay, here's something I got for you. This would be a multiple choice question with these answers. So forget about doing the math. Forget about choosing 2 as your answer. This is a buffer. As soon as you look at this problem and you identify you have at the end weak acid, weak base pair, there's the amounts. Just ask yourself this one question. It's got 3 possible answers, this one question. Question 1, are the amounts of the acid and the base in the buffer equal? If they are, the pH will exactly equal pKa. The Henderson-Hasselbalch equation, if these numbers are equal, they're not, but if they were, the ratio would be 1 and the log of 1 is always 0. What power do you put on 10 to get 1? That's what logs do. So that buffer, if there were equal amounts of the acid and the base, is called an ideal buffer, and the pH is always exactly pKa. The other scenario is what happens if you have a little more base than acid? Forget about the Henderson-Hasselbalch. Remember the question I asked earlier? What does a base do to pH? It raises it. What do buffers do? They keep pH close to pKa. Combine those 2 facts and pick the right answer. Do you want the one that's exactly pKa, the one that's a little above the pKa because it's there, or the one that's a little below the pKa because it's also there? And I have more base than acid. It says so right here. More base than acid. How do you know it's the base? It's got 1 less proton. How do you know this is the acid? It's got 1 more proton. So I'm picking the answer that's a little above the pKa. I did not use a calculator. Boom, there's the answer. Prove to yourself you did not need a calculator to arrive at answer D. I could make any of these answers right, but I would focus on these 3. This is for the students who think the answer, buffers maintain pH near 7. They're going to write that down. And it's wrong. That's not what I said. What did I say earlier? I'm not mad at you. Just, I want to really get this point across. This number is close to what number? 5. What was 5? It was the pKa of the acid in the buffer. Buffers maintain pH close to pKa of the acid in the buffer. Fact. Okay. It will either be right on pKa, in which case you have an ideal buffer with equal amounts of acid and base, or it will be a little above pKa, which means you have more base than acid. What do bases do? They raise pH. Or the pH will be just a little below pKa. That would be if you had more of the acid. That's what acids do. They raise lower pH. Did I say raise? I did. Acids lower pH. So if you flipped these numbers and you had 0.01 moles of base and more acid, 0.015, you'd pick the answer 4.9. You see where I'm going with this? You're going to have a question in your multiple choice like this. In fact, we're going to make up a question right now with a buffer that involves what I call a polyprotic acid. And here we go. I got some minutes. That's good. I'm going to say this. A triprotic acid with these pKa's, 1.8, pKa2, 3.6, pKa3, 11.7 is reacted. The triprotic acid. Let's see. Yeah, I didn't start off on the right foot, but I can fix it here. We'll say 2.0 moles. I'll pick nice numbers, I promise. Is reacted with yeah. I'm just thinking of some good numbers here. 3.8. It's a little high. 3.5 moles. I don't even like that number. Sorry, I'm waffling here. Just want to go back to my previous problem. We ended up with more base or acid. I need a complementary problem. We had more base than acid. I want this one to have a little more acid than base when I'm done. A little more acid than base. 3 gets you exactly halfway. 2.7 moles of sodium hydroxide. What is the pH of the resulting buffer? So right away, you know it's a buffer problem. It's got buffer right in there. Give you a whole blank page with this on it and solve it over here. So you're told you have a triprotic acid. You're given 3 pKa's. Oh, I didn't come up with answers. Don't want calculators. So you're going to need answers. And I'll tell you, I know the answers based on what I put up there. B 1.8, C 1.9, D 3.5, E 3.6, F 3.7, G 11.6. I think some of you see where I'm going with this. 3 sets of answers all centered on pKa's. At least that was my intention. I hope I accomplished it. Okay. So first part is to figure out what you're starting with. I didn't even tell you what the name of the acid was. Triprotic, though. It means that it has 3 protons. Okay. So what's a good generic formula for a triprotic acid? How about H3A, 3 protons on A? That would be the fully protonated species. And when you lose an H plus from that, what are you left with? H2A minus. And when you lose an H from that, what do you think you're left with? HA2 minus. When you lose an H from that, you're out of H's, aren't you? Oops. Which of the 3 pKa's do you think is this one? The most acidic or the least? I hope you said the most. It's got the most protons, and it's a lot easier to generate a 1 minus ion than it is a 2 minus. It's not even twice as easy. It's much more than that. And generating a 3 minus is very difficult. So I'm just going to up here in the question, right? That's the pKa of H3A. Next one is H2A negative. Last one is the one with only 1 proton. There you go. Now, in this question, a triprotic acid 2 moles of it is, which one's the triproduct? This one, or this one? Well, H3A is reacted with, let's see, H3A 2.0 moles is how I started. And we're using 2.7 moles of hydroxide. This is the last time I'm going to draw water. We don't care about water. It doesn't change the pH. I'm going to cross it off and say, who cares? Very cavalier, I know. I only care about the acids and the bases in the buffer. What did you generate when you took a proton off H3A? Oh, it's already at the top of the screen. We started with 0 of each of these. Hydroxide, what kind of base? Strong. Strong base. Must. What's the definition of strong? Here it is. Must react completely. If I had 2.7 moles of H3A, I'd react all of them. I don't have 2.7 moles of H3A. I hope you remember that if you're given a reaction where you have 2 moles of one and 2.7 of the other, and the stoichiometry is 1 to 1 to 1 to 1, you can only react 2 moles in this reaction because H3A is the limiting reactant. And yes, we affectionately call this initial change end, ICE. We'll never do quadratic equations there. I hope that's a relief to most of you. When you reacted 2 moles of H3A, you made 2 moles of H2A negative. I don't care how much water you made. So the only 2 things you have now are hydroxide and H2A negative. H2A negative is also an acid. I know it's the conjugate base up here of this acid, but this acid's gone. It's a new story. It's a new ice problem. New world. You have hydroxide left over. We call that excess, right? And what are you making from H2A negative? You're making HA negative 2. You started with 0. You started with 0.7 of hydroxide. You started with 2 moles of H2A negative. You're doing ice again. OH negative has to disappear. It is now the limiting reactant. You can only react 0.7 moles of H2A negative when you have 0.7 moles hydroxide. You're going to create 0.7 moles of that. In the end, you're left with 1.3 moles of that, and you just created 0.7 moles of this. That is the end. How do you know it's the end? Because you have 0 strong base left over. You've got to keep going until your strong base is gone. I have a mixture of this acid and its conjugate base. I have more acid than base. More acid than base. Just look at the numbers. pH will be equal to the pKa for this acid. That's why we did that work at the beginning. I need to know the pKa of this acid because in this mixture, it's the only acid present. H2A negative, 3.6. So my answer is close to 3.6. That's what buffers do. My only question now is it a little above or a little below 3.6? I'm going to use an arrow. I don't need math. More acid than base. What do acids do to pH? They go down or they go up? The answer is they go down. pH is below 3.6, but very close to 3.6. Only one of the answers is even close to that. And it is the one that is 3.5, answer D. Answer D. And in this problem, I would like to point out, by just manipulating the amount of hydroxide I added, I can make any of these the right answer. And I want you to verify that to yourself when you study this later today. So we're going to be finishing up chapter 4. We only have a couple loose ends on Wednesday, and we're going to finish, I'm pretty sure 5 is a shorty. We're going to finish chapter 5 on Wednesday. I only need 1 segment here and 3 segments in 5. My goal is to have chapter 5 done by Wednesday. And I bid you all adieu, and I will see you on Wednesday.
Doctor, just a quick question.
Sure.
So we came to the 3.6 conclusion just because it reacted 1 time fully. So if it reacted 2 times, it would have been even more towards the 11, right?
Yes, yes. If I had jumped this number up to say 4.7, then I'd be in, these 3 choices would be in play now. Yes, because the H2A minus would be gone, right?
Yep. Thank you.
You're welcome. Good question. All right.